Okay, guys, in this lesson, we're going to talk about numbers that are either categorized as rational or irrational. And both rational and irrational numbers are real numbers. So let's talk about the number sets that we have learned over the years, starting with the most basic number system called the counting numbers. These are the numbers that you first learned when you were 2 or 3 years old and you started counting things. The smallest counting number is 1. So 1, 2, 3, 4, and so on are counting numbers, sometimes called natural numbers. Then we introduced the number 0, and 0 plus the counting numbers created the whole number system. So we have 0, 1, 2, 3, and so on. So counting numbers are also whole numbers, and then when we include 0, we call this the system whole numbers. Then we were introduced to all the whole numbers and their opposites, and these are called the integers. Now notice in all three of these sets, we're not talking about fractions or decimals. So counting numbers are also whole numbers, which are also integers. And then we have the numbers that are fractions and decimals, and these are the rational numbers. Now, let's go back to the counting numbers. So counting numbers, this blue circle, this group of counting numbers is inside the rational category. So counting numbers are also rational. Whole numbers are rational. Integers are rational. Numbers such as fractions and decimals are only rational. They don't have any other classification. Then we have the other group of real numbers called irrational. And these are numbers such as pi, a non-perfect square such as the square root of 3, a decimal that does not terminate and does not repeat. These are irrational. So that's what we're going to talk about in this lesson, and how to identify if a number is rational or irrational. So a rational number is a number that can be represented as a ratio. Notice the word ratio in the word rational. So if we can make a number a ratio, a fraction, where the numerator and denominator are integers, then it is a rational number. Rational numbers can be written as a fraction. They can also be written as a decimal, which is either terminating, means it comes to an end, or it is a repeating decimal that repeats the same pattern over and over. So here's some examples of rational numbers. So make sure you pause the video and write these examples down. We have a fraction, a terminating decimal, a perfect square, a counting number, a mixed fraction, a repeating decimal. So these are only a few examples of rational numbers. Irrational numbers are those numbers that we cannot write as a fraction, where the numerator and denominator are integer values. When an irrational number is expressed in a decimal form, it goes on forever, it doesn't repeat, and it does not terminate. So some examples are pi, square root of 3, and this non-terminating, non-repeating decimal. So let's say that non-perfect squares and non-repeating, non-terminating decimals are irrational numbers. So I would pause the video and write each of these different types of numbers as rational, and then I would write these descriptions as irrational numbers. Now I want to prove why a repeating decimal is rational. And remember, repeating starts with R, and so does rational. So I'm just going to show you the shortcut. I'm not going to show you the why behind the shortcut like I normally do. So this is 2.3 repeating. If it was just 2.3, we would say this is 2 3/10. When you can write a number as a ratio, a fraction, you know it's rational. So here we have 2, and it's not 3/10, it's almost, but it's 0.3333. So it's a little bit more than 3/10. And so I'm going to take the number that's being repeated our 3 and I place it over a 9. So this is the same, 2 and repeating 3 is the same as 2 and 3/9. In our next example, we have 4, and this time we have 090909 being repeated. So you write down the digits that are repeating, and how many ever digits are repeating is how many nines. Now I'm going to go ahead and simplify this, make it look a little bit neater. So I'm going to simplify 4 and 1/11. So again, if I can write it as a fraction where the numerator and denominator are integers, it is rational. Our third example, we have 3 numbers, 3 digits repeating. So I put the digits that are repeating in the numerator, and then I put how many ever digits are repeating, that number, that amount of 9s in the denominator. So these 3 repeating decimals are rational numbers. You'll have to excuse my puppies. Girls. Okay, so I want to go through each of these and I'm going to write them as rational or irrational, and I am going to express how they are indeed rational by writing them as a fraction where the numerator and denominator are integers. So the square root of 12 is non-perfect, so this is irrational. -3 is rational because I can write that as a ratio by putting a 1 in the denominator. Pi is a non-terminating, non-repeating value that goes on and on and on, so it's irrational. 2.173 is the same as 2 and 173 thousandths. So ends in the thousandth position here, and this is a ratio, a fraction, so it's rational. My next example, -3.276 ... This means this goes on forever, it doesn't terminate, and it doesn't repeat. It is irrational. The square root of 49 is really 7, and then of course we can put that over 1. It is rational. Negative square root of 196 is really -14, and we can put that over 1, creating a ratio. -2 times pi is irrational. The square root of 400 is a perfect square. We can write that as 20 over 1, proving it is a rational number. 5/12 repeating is rational. We can say this is 5 and 12 over 99. -2/3 is already in its rational form. It's a ratio. We have 4.12, which is 4 and 12 hundredths. We have 4.5 repeating, which is 4 and 5/9. We have the square root of 1/9. The square root of 1 is 1, and the square root of 9 is 3. 3/7 is rational. 7.1345 is non-terminating, non-repeating. Negative radical 3 is non-perfect square. 2 radical 3 is a non-perfect square. Now pi over pi, those are not integers, but it can simplify to 1 over 1. So that is rational. And then we have 21, and that's equal to 21 over 1. So it is rational. So these are examples of rational numbers. I can write them as a fraction where the numerator and denominator are both integers. Irrational numbers cannot be written that way.